Good morning, my name is Adele and this is Sidi, Ahmed, and we are students from Kyushu Institute of Technology. Today we have the honor to present to you our mission idea entitled Low-Cost Communication Network for Equatorial Remote Areas. So essentially, this is the outline of the presentation. Introduction or how significant our idea, our mission objective, the concept of operation, orbit and constellation design, of course, the mission key parameters, the space segment design, and the implementation plan, as well as our conclusions or possible results. So to start with, as we all know, there's a vast increase or tremendous increase in the telecommunication globally. However, based on the review of Peer Research Center, they said that the global situation access to communications varies from as low as 3% to 80%. 3% to the developing countries and 80% to the developed countries. So there's a huge gap between the access to communication between developing countries and already developed countries. And they say that the ownership, they have access, but sometimes they don't own a computer or don't own a smartphone or mobile phone. And when they interviewed these people, they said that 90% of these people use this simple mobile phone only for text messaging or for simply sending simple data. However, to validate these statistics, we also made our own research. Okay, so we downloaded the population data from the socioeconomic data from NASA and then plotted it with the people with access to communication and people that don't have access to communication in the plus and minus 10 degrees. And we found out that out of the 1 billion people in the plus and 10 minus 10 degrees, about 103 million don't have access to communication. So these people are mainly located in South America, Central and Southern Africa, the Southeast Asia, and the Pacific Islands. So you can note there that there's shaded colors have access, but those areas as entire as the Indonesia don't have access to communication or limited access to communication. So we now know the need. They don't have access. They are developing countries, and the access is high. Okay, so mostly these people are disconnected. So the potential solution to provide communication via networks. So how to solve? Either we can make a wire or mobile communications, which of course fast and easy, but limited coverage, particularly to remote areas. But we can also provide good quality service by communication via satellite, but of course this is expensive. So our question is how to provide this SMS or data communication with a relatively low cost for developing countries along the equatorial region. So in QTech, there are international students from developing countries to emerging to already developed, from Indonesia, Philippines, Mongolia. And we come up with this idea of low-cost communication network for equatorial remote areas. So our mission simply to provide or to demonstrate the satellite constellation in equatorial region for providing stand-alone communication, provide services at a low cost. So how we do that? This is the mission concept. So essentially, we have three segments: space, ground segment, and user segment. The space segment consists of 4 satellites orbiting along the equatorial region. We have the ground segment. We have 1 control station and 6 ground supporting stations. Okay? And we have user segment, which will be either LAN network or local network or portable subscriber modules. Say, for example, we want to send a message from user red to user green, here encircled. And then when the satellite passes, you can send data to the satellite. And then this satellite will then pass this data to the nearest supporting ground station, and then we'll transfer the data and put it in, or send it to the network via internet to the control ground station. Then this control ground station will send this data to our network until it reaches the desired local network. Then transmit this data and then reaches the subscriber. And this sequence, or this, can reach until 28.3 minutes. However, if the user would like to send, say for example, user Red would like to send information to anyone within the network, then we can utilize the existing mobile networks. So to continue, I would like to ask Sidi.
Thank you very much. So, dear everyone, so my name is BENDOUKHA Ahmed. I'm a student from KIT, Efficiency of Technology. So, what my friend that said, so respecting and following the previous slide, that is what she said. So we will now this part, just we will talk about technical part. So before talking about technical part, so we should specify and analyze the orbit and constellation design. So we have 2 points more important. So we had the Earth coverage in terms of latitude. So we choose the field of view about plus minus 50 degree. The latitude for coverage is less, or it can be degree, plus minus 10 degree. That's respective number of population choose. So the second point is the time delay. The time delay, we choose 1 hour, so about 60 minutes. So computed based on following. So we need the altitude about 1,000 kilometers. The number of satellite. So our constellation is with 4 satellite, and number of ground station 7. So from minus 80 to 150. So including the ground station master. So for the controlling. So this figure just so by using STK, so the location of different ground station and 1 ground, so 6 ground station plus ground station for controlling. So the next slide dependent of the altitude. So we will now show how to choose this altitude, field of view, by analyzing and do some calculations. So we can see in this table, dependent of altitude and field of view choose. So by varying the altitude and the field of view, we can see the red value, it means the latitude, its physical maximum, depend the current altitude used. And the blue line, it means different consideration by varying altitude we can fix. This value of the unit is in degree. So we can see at 1,000 kilometers with field of view of 50 degree, we have more than plus 10 degrees, so 10.9 or 2.4 degree. So now the reverse time is more important for the ground station by using this satellite. So in this calculation we do for different satellites. For example, we use for 10 satellite, varying field of view also, the altitude also. So we can see in this line, the blue column. So at 1,000 kilometers and with 4 satellites in our case, the time revising time 28.3. So we can use, if we know the field of view, we can compute the reverse time. This is for our payload use. So this table just shows the time delay for transmitting message between the user. So we can see with 4 satellite and 7 satellite, we have at 7, so we have 59 for minutes. So in this case, we select this time delay as 1 hour. So the cost analyzing, the cost analyzing. So before analyzing, I specify the parameter orbit and design. We just estimate the cost of 1 satellite is about $2 million. So for 4, it's just multiplying by 4 satellite. So the cost of 1 ground station about $50,000, $100,000. So without operation of so if we include the operation of the ground station, maybe we can add $40,000 or $50,000. So we can see in this table the cost in $1 million. So we have number of ground station. So in this case, we have 8, and number of satellite. And we can see in 4 satellite, if we have 4 satellite and 7 ground stations, so the cost it can be $10.45 million. So the next. So And the efficiency also is more important for our parameter orbit design to find the cost. So we can see here the efficiency we can compute it by using this formula. So it's that's one. If we know the cost and time delay, we can compute the efficiency. So we can see if we choose just one ground station and one satellite, we can see the efficiency is very good. But in our case, it's not. This is our aim. So in our aim, we use constellation with 4 satellites and with 7. So we can see the efficiency it decrease, but respecting to our requirement. So now we talk about the K performance parameter. So we have one part more importance about coverage area and message delivering time delay. So from the table we fix 60 minutes as time delay plus minus 10 degree, and the release time is 28.3 minutes for all satellite. So the data capacity is more important, depending on the transmitter use. So in our case, we use just data rate about 200 kilobits per second. So for SMS size, we select the maximum for one SMS is 1 kilobyte. And the capacity of one satellite is about 25 messages per second. So listed K performance parameter, depending on the ground station. In this case, the K performance is more important for the ground station and the user. So for the ground station, we have some parameter and value we can see here. If in the ground station we use like parabolic dish antenna with high efficiency with 65%, and antenna is about 30 decibel. Considering the receiver sensitivity and bit error rate about 10-7. So for the user, so in our case we use 200 kilobits per second for like bit rate, but in case of user we have two cases. In case we use internal antenna, so we can reach the bit rate about 384, so for sending the data from the user satellite. In case we use portable, not local network, portable, like carrying like portable, so this portable have another antenna, is external antenna. So if we connect with the external antenna, the bit rate can be 1.5 megabit per second. So now, to achieve our system, the communication, we propose two suitable communications. So we use S-band and VHF band. So with this, we can compute and dual-link budget for uplink, downlink. So we can get the margin about 20 for S-band, and for VHF about 30 for the margin. Just we know the C over N0, theoretical minus the requirement. So for the common data handling, it's more important to know the memory of our in the board of satellite. So in this, we decide for very reliable and redundant data storage. So if we use 200 kilobits per second, kilobits yes per second, we provide 25 seconds in 1 second, message per second. So about 2,160,000 messages in 1 day. So equivalence, we need memory about 2.16 gigabyte transmitted per day. So our system use also attitude control system. In this case, we use 3-axis stabilization, and also consists of 3 parts. So we can use sensor, like 3 gyro, 1 GPS, and sensor, microcontroller just to collect the data, and magnetometer. So for our power system, the power system shall be reliable and shall include redundancy. So the satellite power consumption we estimate about 100 watt, and the margin about 20 watts. So the total just summation of this value. So the mass budget, the satellite mass requirement, so it's less than 50 kilogram. We propose like 40 kilogram. The payload is about 10 kilograms, our transponder. So the implementation plans is more important part. So in this case, we want to build our ground station, for example, in this country. So we need like agreement. So how to do this collaboration. So in this implementation, we have some factors. It consists as several steps. So we have technical part, we have law regulation, and we have source provider. So for technical, we need investigation, development, and production of this service. In case of law regulation, we need permission, and second one also we need license to allocate our band by respecting the ITU, International Telecommunication. For service provider, we need local government and also the local network provider. So this scheme just show the life cycle of our project decided by our team. So we decided that to start from September 2015 till 2017. So we start by the ground station conception, so including VBM and half part of EM. And half part of EM and FM, we focus in the hardware and software plus interface and operator training. So finally, we conclude by conclusion. So the opportunity for space satellite set is good for developing culture and solving regional problem by the effort from international country. And the main purpose to having minimum cost. This is our mission. If we cannot reach the low cost, it's not. So in the Equatorial region, of course. So the development of this ITA can be performed by lean satellites. So this is what it's used now, and maybe we will discuss about this lean satellite in discussion group. So because our mission is talking about low cost, so it's good advantage and unknown technical capability for our mission idea. Okay, thank you very much. This is our team for.
So I'd like to confirm that the inclination of the satellite is 0 degree or plus minus 10 degree?
The inclination we fix in the equatorial plane is 0 degree, of course.
Is 0 degree,
But
okay.
the latitude we fix plus minus 10 degree. The
Okay,
latitude
okay,
is
okay,
plus
okay.
minus 10 degree.
Okay, so maybe the most difficult thing is to get a launch opportunity, because maybe it's very difficult to find opportunity to launch your satellite into the 0 degree, but not geosynchronous orbit. So how you can find that?
So yes, it's a good question about launch, because we decide about our team to just we choose which launcher can be used. So we cannot know exactly which launcher can be used. So because it's more difficult in the equatorial plane.
Okay, you're right, sir. The launch would be more important. However, we also have this, as shown earlier. We study the latitude in terms of latitude and the number of field of view. We can adjust on say for example, the the height of the satellite or the inclination of the satellite, and we can make this system, but it's maybe the target area would be along the equatorial region.
So when you say a low-cost communication, what's the price per message?
How low is low? That's a good question, sir. Okay, but this low cost is relative in terms of, say, for example, the existing maybe global star or inverse. Okay, the low cost is like because we have a simple system and we use only 4 satellites and 7 ground stations. And based on our cost analysis, okay, we can provide these good services only we can increase the number of satellites, or we can either increase the number of field of view. But however, in our analysis, we just get the median on wherein we can provide these services, but with considering the number of ground station and the number of the satellite that we will going to launch. So the system in itself is relatively cost, but it can provide the simple service that these people would want.
So the cost versus the service level is something that you have to balance. So I saw the time interval between the communication is 60 minutes, an hour. Would that be? Do you think it's acceptable for texting services such as SMS?
So the time delay it's about 60 minutes. But because we do some calculation, I show in the previous table. So we do some calculation, not just for, in our case, we choose 4 satellite and 7 ground station. But in the table, I show maybe 10 satellite and different ground station. So just we do some calculation, respecting our latitude, and after we decide for the time delay, it's about 1 hour. So respecting how the revis time we have, that 28.3 per minute. So between 2 visit ground station bypassing all satellite, the 4 satellite.
So that will be reflected on your price.
Yes.
That's so. If you enlarge the interval between the two, then
Because
of course you have much less number of satellites, therefore low cost. However, if you look for better service level, then of course the price goes up. So that's something you need to balance.
so in case, because if we increase the latitude and number of satellites, so the cost it will be higher. So this our mission we just fixed, and we need to focus just in the low cost. So this is the more important. So we can reach more, but you should respect our cost. This is the more important.
We can make our system as complex as we would like to want, or we would like to have, but we're thinking of something that somehow it can provide the right service at maybe that will compromise the efficiency as well as the time delay. So if maybe the providers or resource person can maybe grant us these resources, then we can increase our time delay. Or maybe we can use other possible approach in the future, like making some CDMA approach wherein we can have two-way communication, so we can make this delay of the data shorten, or we can increase the number of the satellite. But if given that we don't have the resource at the moment, we fix ourselves to 4 satellites and 7 ground stations.